Buddy? No, you don't have to laugh at this joke, but
Controls your grades. Yes, you do.
yeah, I control all of your future. Okay, so here's your joke to start the lesson. Blonde walks into a bar and says, "Ow." Okay, that's it. All right, so if you're not laughing, maybe you're blonde and that's why you don't get it. Okay, so like literally a bar hits her in the forehead. You know what I mean? Walks into a bar and says, "Ow." Yeah, everybody check their hair color. Okay, polar function graphs. A bar, like not a restaurant bar, like a bar, like she walks into it and beats her face on a bar. Yes, I can see that you are blonde. Yes, we see it. Yes, we see it. Okay, stipulation 1 was that we get right back to work. Okay, number 1. Rather than try to use this list of points here on this notes and this tiny grid, I went ahead and given us a lot more space and a larger grid. And yes, I did make these grids. I made these grids as well, but they weren't big enough, so I made something separate. Now, I would expect you to be able to do this stuff without a calculator. Cool? Now, I will graph it on the graphing calculator just so you can see what it looks like. Normally, I would do it on Desmos, but the computer's right now it's recording the document camera, not my computer screen. So if I switched over to Desmos, it wouldn't see it. I'm going to go ahead and put this thing in polar mode so I can graph on here just to prove the point. Oh, you know what? And zoom square is number 5. Okay, good. There. So when we use the graphing calculator, that's what I'll do to show the images. Cool? Okay, here's what we're going to do. We want to plot a lot of points because we're not just trying to memorize what these graphs look like. Now, we could just say, here's what they look like, and do your best to memorize it, but I'm not that kind of person. My memory is awful. Maybe I've walked into one too many bars. I don't know. And you can take that however you want to, okay? But my memory is not great. So I'm thinking, how in the world am I going to graph r equals 4 sine theta if it's not going to be from memory? Then what I need to do is I need to plot a bunch of points, which is true for any new thing that we're graphing, right? Unfortunately, without a calculator, some of these things that are in this grid have radicals in them. Oh no. I don't know what root 3 divided by 2 is, and I don't expect you to know what root 3 divided by 2 is. But it's one of these points. And I was trying to figure out what the best way to do this was, and that's when I realized, avoid radicals. Just avoid them altogether. And there are what I like to call pretty points for sine of theta. There's 8 of them, in fact. Those 8 represent the 4 quadrantal angles, because sine is equal to 0, 1, and -1 on the quadrantals. And then the other 4 points are all the places where sine is equal to positive 1/2 or negative 1/2. Those are pretty enough, because we know what 1.5 looks like on a grid, right? Because we will have to do 1.5 on the second example. But let's draw ourselves, I don't know my unit circle, so let's go ahead and draw our 4 triangles. This also has the quadrantals on it, if you couldn't tell. But let's draw the 4 triangles that are going to give us the value of 1/2 for sine of theta. In order for it to be 1/2, you'd have to remember that sine is y over r, or opposite over hypotenuse. So that means it's going to have a 1 here, a 2 here. Hold on, I'm going to try to type my pen. 1 here, 2 here. Down here, -1 and 2. -1 and 2, and I'm hoping that you all know what the size of the reference angle is in this image. 30 degrees, good. So we're going to put a little 30-degree angle in every one of these, or just in one of them, who cares? The point is, these are the 30-degree reference angles, and 30 degrees in radians, because we're going to do everything in radians, if you couldn't tell, all radians. 30 degrees is pi over 6 in radians. Now 2 pi is coterminal to 0. So normally you wouldn't include that point. I'm going to just for continuity's sake. It just felt like I needed to. Okay? And I have a lot of vertical space, and I plan on using it because we have 8 coordinates to substitute into. We have thetas as our inputs, leave a space for a little bit of work, and then r. In the future, there will be a table here so that I don't have to tell my students to leave space, but I made this hastily because I needed to send it to print shop immediately so I could get it back in time. Okay. And I don't know how far left and right to space it out, but I do know I'm not going to go that far. I'm going to go with theta is 0 radians, and then pi over 6 radians, because that's the first 30-degree triangle, pi over 2. then the fifth pi over 6, and finally pi. Now I do want to do the other side. It won't have as many points. I guess I said 8 points, but I'm going to have 9 since I'm doing 2 pi. But 2 pi is going to be the exact same coordinate as 0 radians. Cool with that idea? So down here again, I've got another theta. And then what's after pi? 7 pi over 6. And then 3 pi over 2. The 11th pi over 6. And then finally 2 pi. And whatever value I get for r at 0, I can just go ahead and write in, leave a space. I can go ahead and write it in for r at 2 pi because they're coterminal angles. So far so good? Yes, fantastic, great. Okay, let's go. I'm going to do this one all in blue, just because I'm holding the blue pen. Let's substitute 0 into this. Well, sine of 0 is y over r. I have no y value here, so sine here is, well, 0. So this actually says 4 times 0, which gets us 0. That is the r comma theta coordinate 0 comma 0, also known as the pole / origin of the polar coordinate system. There it is. That was kind of anticlimactic. All right. Pi over 6, right here. Sine here, y over r, gets us 1/2. So we have 4 times 1/2, which is 2. That is the r comma theta 2 comma pi over 6. By the way, these diagonal lines that go around, those are called the spokes. I didn't make that up. They're called spokes. Okay? So we're going to go to the pi over 6 spoke, out to the second ring. That's right here. Do not connect those dots with a straight line or anything like that. Thought exercise, just for a moment. You've had questions like this on tests in the past. In fact, probably just this last test. Imagine for a moment, if you would please, that this angle was half the size. Let's imagine it was a 15-degree angle. Would the vertical side of this triangle be smaller or longer than what you're currently looking at? If this angle got smaller, would this dotted line be longer or shorter? It'd be shorter. So since this vertical line would be shorter, that means my sine value is smaller. Is everybody cool with that? So if I was at a smaller angle, imagine I was at this, which happens to be half of pi over 6, which is the pi over 12 spoke, 15 degrees. We would be smaller than this. So it would be somewhere here-ish. And I typed it on my graphing calculator last period. Sine of 15 degrees was like 0.25. So if you do 4 times that, you're right around the 1 mark. So it's somewhere right around here. Why am I telling you this? Because what I need you to see is that this wasn't jerky. It wasn't a straight line. It actually is a nice, smooth, arching motion like that. Cool. Okay. Which happens to be in a counterclockwise motion, which happens to be the way that angles are read. So I just wanted you to see it that way. Great. Pi over 2. Sine at pi over 2, well here y and r are equal to each other, so it's 1. That gives me 4 times 1. The r theta is 4 comma pi over 2. So on the pi over 2 vertical axis, go up 1, 2, 3, 4 rings right there. Now 5 pi over 6 here is the reflection of pi over 6. Sine gets me the same, can get me the same values in quadrant 1 and quadrant 2 because y is still positive, right? Sine here is 1/2 again, so I have 4 times 1/2, which gets me 2 again. So that is 2 comma 5 pi over 6. So go to the 5 pi over 6 spoke, and you're out onto the second radius. I have so much trouble with this. Where's the second radius? Right here. It's not an accident that that coordinate, or coincidence, is a reflection of that coordinate. Because around the unit circle, those 2 dots would have been reflections of each other. Does that make sense? Okay, cool. And at pi. Sine of pi, once again, when you're on this horizontal axis, you have no y value, so sine is 0. So you got this 4, 0 going on, which gets you 0 comma pi, and that is, well, hey, it's here again. That's neat. And we said that 0 is coterminal to 2 pi, so we know that's going to happen. Now, last period, actually, before I say that, I'll just keep going. Let's plot this one. 7 pi over 6, okay, finally, we're going to dip into the negative sign values. Something interesting is probably going to happen here, right? So we've got sine is negative 1/2 here, so we have 4 times negative 1/2, which gets us -2. So this gets us the opportunity to review how to graph polar coordinates when you have negative radius. So go to the 7 pi over 6 spoke, and because I have a negative radius, I do not get to stay on this spoke, at least here. I have to reflect 180 degrees away from here, onto the second ring, which means right there again. Oh, well, that coordinate just repeated itself. Okay, at 3 pi over 2, sine is -1, because here y is negative, but r is always positive. So it gets to be 4 times -1, a radius of -4. Okay, so go to the 3 pi over 2 zone, just here, but reflect 180 degrees onto the fourth ring. Oh, interesting. And then, by golly, that one happens again, but this time it's the reflection of this triangle. So sine is still -1/2 here. So you would go to 11 pi over 6, but you don't get to stay here. You have to reflect away because negative radius onto the second ring. Dang. And you already know what's going to happen here. So what is the shape actually? If I had shown you where the pi over, what am I trying to say? If I had shown you where the pi over 4s and the pi over 3s were, then you would have gotten a clearer image. Let me show you exactly what it would have looked like. Y equals 4 sine theta. It's a circle. We graphed the only 4 rational coordinates that that circle has. Every other coordinate on that circle requires a radical of some sort. It has exactly 4 pretty points. We went around that circle twice. Isn't that interesting? And I think it's important that you mark where you started and the direction and the number of times that you went around, because I know what's coming up in the next lesson. Do your best to draw a circle. It's a sketch. Ooh, man, I missed my pole. Crap. Well, whatever. You know it was supposed to go right through the origin. Students last period said that an X would be a good way to show you that that's where I started. Do you agree? I feel like I should just put a circle around it. I don't know. They said an X marks the spot as good. And it went this way. And it happened 2 times. That's interesting that we went around it twice. Very interesting. I wonder why. You don't have to answer. We're just wondering why, right? If you needed to know, if you had to convert this back to rectangular coordinates, quit playing with those squishy toys. Dang. Anyway, if you needed to know and you had to put this back into rectangular coordinates, which again is great review because we just did that, you would have to multiply both sides of this by r, and what you would get is r squared equals 4r sine theta. You would remember that x squared plus y squared is r squared. You would remember that r sine theta is y in rectangular coordinates. You'd bring it all to one side. I'm running out of space. You never know when that might be a multiple choice answer to something. And then technically you would need to finish up by completing the square. And what you would get when you complete the square is this. X squared plus y minus 2 quantity squared equals 4. That is the circle if you were in rectangular coordinates, which doesn't make any sense in polar coordinates. But if you were in rectangular coordinates, that would be a circle with its center at 0, 2, which would have been right there, with a radius of 2. See, if I was right here, I'd go up 2, and I'd go down 2. Yes, ma'am? Where did I get this 4 from?
The 4y.
It's the so r sine theta. Remember, sine theta is r over y over r. If sine theta is, how about I just write it out and tell you? Multiply both sides by r. So it was from actually lesson 13, the last lesson that I don't have a video of right now. And so I just was converting really fast because it's actually older material and I'm not asking you to go through that in this process. But I did wanted you to see it, that's how you would pull that off. Neat. Yes, Nolan.
Did you get the first 4?
This 4 here?
That one.
So if you complete this square, you cut this number in half. negative 2, square it, plus 4. But if you add 4 here, you have to add 4 here. And then you'd have y squared minus 4y plus 4, which factors to that. That's where that 4 came from. But I just needed you to see it. That way I could tell you why the center was 0, 2 in rectangular with a radius of 2. I just wanted you guys to know that stuff. Now, if we come down to the actual notes, you'll notice that this didn't go to 2 pi. That's because I already knew what the shape was with 1 pi instead of 2 pi. Interesting. Let's just throw this on here to the best of our ability. We were here, and then up 1, 2, 3, 4. We were here, and then we had pi over 6 comma 2, and 5 pi over 6 spoke also on the second ring. Doing our best. See how small this is? This is why I messed it up twice when I was trying to do it on my own with these grids. There. So just go around that circle twice. Neat. That's it for that example. My idea for this lesson is that when we go through and plot all the coordinates, we will start to build patterns for ourselves. And once you have noticed the patterns through discovery, you'll be much more likely to be able to remember those patterns. That's my hope. Rather than me just telling you these truths, I'd like for you to believe them because we did it together. Ready for the second example? Oh, I wrote, anyway. Ready for the second example? All right. Maybe we should put, this was 1a, because this is our notes companion, let's call it that. And this will be 1b. In class period, I accidentally messed up and wrote 2. But that's clearly not example 2. It's example 1b. This one was r equals negative 3 cosine theta. All right, now, don't answer me. I just want you wondering to yourself, I wonder what this shape will look like. And I wonder which way it'll rotate, or not even rotate, but travel through its coordinates. Because hopefully what's obvious here is that the function changed from sine to cosine. And hopefully here it's obvious that the number on the front is now negative. Let's see how that affects our system. I'm going to do the same 9 points. Unless you think I should just do, should I bother with 2 pi? Or should I just not bother with 2 pi since it's always going to be the same coordinate as 0? Just don't? Okay, so if we don't bother with it, on the top, don't go out to pi. In fact, we should probably talk about the pretty points. There are still the 4 quadrantals, and then there will still be the 4 places where this function could equal 1/2. But cosine equaling 1/2 is not in the same place as sine equaling 1/2. If you look at these triangles, cosine would have been root 3 over 2. Well, I don't know what root 3 over 2 is. So I only want to plot the points where I can get integer or rational values. So see, if cosine is 1/2, it's x over r. Oh. In these triangles, the vertical side is going to be root 3. So what's the size of these reference angles? These are 60-degree reference angles. Cool. You know what? I'm not even going to bother writing in all of them. We get it. They're all the same size reference angle. They're all 60-degree angles. Those are the pi over 3s. So we've got our thetas. Across the top, we'll do the first 4, including 0. So that'll be theta is 0. Theta is the first pi over 3 reference. Then pi over 2. Then, was this 2 pi over 3. Leave a space for a little bit of work, and then write r. Below that, we've got the next set of thetas. They will begin at pi, then, which is actually 3 pi over 3. Then we've got 4 pi over 3. 3 pi over 2. And help me. 5 pi over 3. There. Oh, the symmetry makes me happy. That makes me really happy. Let's see what we got going on. I'll do all this work in green. If you can remember, hopefully you can, or maybe not, I think about the cosine wave when I think about cosine of 0. I know it starts at a maximum of 1, but you could also say if you're right here, your r and your x value are equal to each other, 1 over 1. So cosine of 0 is 1. This gets me -3 times 1, gives me an r of -3. So this is the r theta of -3 comma 0. That means 0 on the third ring. Oh, but you have to reflect away from here. That's right here. And like I said, last period told me X marks the spot is a good place. So that's just telling me that I start there. I don't know, maybe I should have done an arrow or a red circle or some sort. But the point is we're starting there. That's our starting coordinate. Interesting. Alrighty, pi over 3 puts me here. Cosine's going to be 1/2. Remember, the whole point of doing it this way was that way we were dealing with rational things only. And half of -3 is -1.5. Now hopefully you made a prediction already about which way you were going to rotate. Let's find out. Go to the pi over 3 spoke and reflect away from it. Down here somewhere. -1.5 rings. So 1.5 rings on the 4 pi over 3 version of the spoke, right down there. So as it turns out, we're still going counterclockwise. All right. Pi over 2. Here, you have no x value, so your x over r is 0. Pi over 2 comma 0 is right there. The pole, the origin. Now 2 pi over 3 is here, where sine is -1/2. So I have a positive radius. Go to the 2 pi over 3 spoke, and you get to stay there since radius is positive, and it's on 1.5 rings. 1.5 rings. Oh, look! It's the reflection of this dot over the x-axis. Neat. This one that dealt with sine had dots that were reflections of each other over the y. No, excuse me. There's no x and y axes in polar. I am so sorry. These two are reflections of each other over the vertical axis. Let's use directions. These two are reflections of each other over the horizontal axis. Just like how the x-axis in rectangular is horizontal and the y-axis in rectangular is vertical. And Leah, you asked me a minute ago, remember, see how the sine of theta deals with the y values in rectangular and was symmetric over the vertical axis? How about that? Where cosine of theta in rectangular is that. So x is r cosine theta. It is symmetric over the x-axis in rectangular. Is it not? Yep. Okay. Because, look, -1/2, -1/2. Neat. Alrighty. Cosine of pi. You're here. It's -1. Oh, I forgot to write my r, didn't I? -1. So I have -3 times -1, which gets me +3, which is, I'll be darned, there again. And guess what these coordinates are going to be? Actually, that'll be +1.5, won't it? 4 pi over 3, shouldn't try to do it from memory. -3 times -1/2. Get you +1.5. There we go. 4 pi over 3 spoke, +1.5. It's right there. Yep, get to stay there. 3 pi over 2, cosine here is 0 again, so I get 0 once more. I feel like something went wrong. Oh, no, it didn't. I'm all right. And what is this? What did I say it was? 0? Yes? Right? No, it's not.
Yeah. That's the vertical line.
I swear I'm smart. What is it doing? Here?
Yeah,
there's no x value. Okay, so we're good. And that puts us 3 pi over 2 comma 0 is right there. And then lastly, 5 pi over 3 is right here. This is going to be the 1/2 again. So I have 3 times 1/2. It's the reflection of... What is happening right now? There. It's this one right here. The reason why you don't see me going 2 full circles is because I didn't do 2 pi. So what happened? It did this. And do your best to draw the circle. Like that. Oh man, I missed the dot again. There we go. I'm doing my best. We went counterclockwise, and we happened to go around 2 times again. Like that. So we're around twice. Neat. This one's a circle whose, if you were in rectangular coordinates, center would have been on the x-axis. I do want to show you what that equation would have been. Now, once again, you'd have multiplied both sides by r. So you would have had r squared equals negative 3 r cosine theta. R squared equals negative 3 r cosine theta. X squared plus y squared equals negative 3 r cosine theta is x. You'd add 3x to both sides. And for this, you'd need to complete the square. You'd cut this in half, and then you'd square that number, and you'd add to both sides. This would then be factorable. I've run out of vertical space, but I don't feel like writing over here, so I'll just keep writing here outside the box. And this is what you would end up with. X plus 1.5 quantity squared plus y squared equals 2.25. So why did I bother? Because I needed you to know that if you were in rectangular space, this thing would have had a center of 0, negative 1.5 and a radius of 1.5. Because now we're going to talk about some patterns of things. And just to prove the point, we'll go here, and I'll change it to negative 3 cosine theta and hit graph, and whee! And you might have noticed that it colored that circle, right? But I'd like you to see that it went from 0 to 2 pi. I could have changed it to pi and then seen that I got the exact same image. So what you didn't see happening was this thing traced itself twice. It's actually really hard to see. If it was bigger, it'd be easier to see it happen. So how would I make it bigger? Well, if we had noticed the pattern, maybe you might have noticed that the number in front of my cosine being smaller made the circle end up having a smaller radius. Did you notice that? So what I'm going to do is I'm going to increase the radius size, and I'll change it to a much bigger thing, and if we're lucky, we'll be able to see it color itself twice. Oof. I could see it, but I don't know if the video caught it. Try one more time. How about we go to 12. Yeah, I'm going to change it right now. Yeah, so what I said doesn't even make any sense, does it? It looked like it did it. Let's see if we can see it traced twice. What did I type wrong? Oh, goodness. Let's try that again. Dang. Yeah, if you were looking at on my calculator like I was, you could have seen that it actually did color over itself 2 different times. I wonder. No, I don't have a way of doing it. I was going to say, I wonder if I could restrict the domain. Let's see if it'll do it. Yeah, so it just traced over it a second time, but that's not believable. You can't see it happening. Wish I could show Desmos on the video. Won't work. Oh well. All right, let's see. What do we know now? So we come back to this, and we were here on the third ring. We started there. We had a coordinate of what was happening next. This one here, which was down here. So we were on the 4 pi over 3 spoke at 1.5. That's here. Then we were on the 2 pi over 3 spoke at 1.5. And the rest of them we said were irrational. So we got this circle right there. It started here, and it went this way, and it went twice. So you might have noticed most of the real notes are happening on the companion. So let's see if we can draw some conclusions. If a polar equation involves only r equals a sine of theta or r equals a cosine of theta, I'm hoping you can tell by now that your graph will be a circle. See that? But can you describe the direction that we graphed? What did you notice about these graphs? You could say it. Blake, what do you got? Counterclockwise. So they both graphed counterclockwise. Whoa, how do you spell clock? There we go. They both went counterclockwise, which shouldn't be surprising because that's the way angles read, right? But what else is it asking? It's also asking about the location of said circle, which we'll highlight more in a moment, but what do you think that positive 4 did that would have been different if it had said negative 4? Or what do you think this negative 3 did that would have been different had it said positive 3? Because I don't know about you, but the first time I was doing this, I kind of thought that this negative might make me go clockwise instead of counterclockwise. That's just what my prediction was. Of course, I was wrong, and that's okay. But that's what I thought it would do. Okay, what are the similarities between the two graphs? Well, obviously they're both circles, right? But how about we say they're both centered on an axis? Instead of saying centered, how about both say symmetric over an axis? Did you notice that we could predict the size of the radius of the circle? You didn't catch that? This had a 4 on the front. Its radius was 2. This had a 3 on the front. Its radius was 1.5. What's the size of the radius? Half of that number that sits on the front. So if it's an A, then the radius is half of A. Yeah, the diameter is A. Yeah, the radius is half of A. They both also went around their circle twice. So they both completed 2 circles. But what are the differences? Well, I said they're both symmetric over an axis, but they were symmetric over different axes, weren't they? R equals a sine theta is symmetric over the vertical axis. Don't call it the y-axis. There's no x's and y's in these. It's the vertical axis. So what do you think the negative would have done if I had made the 4 negative? Negative 4 sine of theta. How about that? What if I had made it positive 3 cosine of theta? How about that? So this direction thing tells you which side, quote unquote, that you should be on. The upside or the downside, or the left side or the right side. Interesting. So if we said r equals a sine theta, positive a above horizontal, negative a below horizontal. Then you solve for cosine. R equals a cosine theta. Positive r, no, positive a, excuse me, right of vertical. Negative a, like we had, left of vertical. It's so difficult not to call those the x and y axes, but they're not. Oh, I forgot to write that r equals a cosine theta symmetric over horizontal axis. I think that's everything that we talked about last period. Unless you guys can think of any other similarities or differences, happy to hear them. Make a good video if anybody else saw anything that I didn't see. No? Okay, one last thing. It says, give the ordered pair r theta of the point that is farthest away from the pole / origin, and how is it related to the equation? I'm actually going to say, instead of how is it related to the equation, I'm going to say how is it related to the function. Not the polar equation. I'm going to talk about the rectangular function. For r equals, what color have I not written in on the sheet? Green. For r equals 4 sine theta, we were furthest away from the pole right here at 4 comma pi over 2. How is that related to a function? Watch this. Y equals, and it's not an accident, I'm using rectangular coordinates, y equals 4, crap, bad videos. It's bad for my video. Y equals 4 sine x. In the first period, guess where its maximum is? It maximizes at x equals pi over 2. And since it has an amplitude of 4, it would have been 4 away from the x-axis. So that's how they're related to the function that they represent. And if you weren't using r's and thetas instead of x's and y's, if you think about the wave 4 sine x, it has a maximum value at this coordinate. And then the other one, you guys are packing up like the bell is ringing. The other one, r equals -3 cosine theta. It was furthest away right here. And we could say that was at more than one place, but that was at what? 3 comma pi? No, it was -3 comma 0. But 3 comma pi also. I want to say 3 comma pi. And here's why. Because if you relate that to the cosine wave, it has a maximum when x is pi. And the max value would be 3. So it's very interesting. If you had to think about on a polar graph, the furthest part from the pole would be where the xy wave has a maximum value. Isn't that neat? Also, where it has minimum values as well, because the graphs, the waves, their minimums and the maximums are the same distance from the x-axis. So on the second rotation around, dang, video goofed up because of a bell. Thanks, guys.